Morning, everybody.
Morning. Hi.
This will be a presentation on our senior design project. Our team name is Codec, and we are presenting to you a highly secure software platform that supports smart locks. My name is Isaiah Page. I'm going to be the project leader for this team, and I'm an electrical engineer.
My name is Marcia Rivera. I'm going to be the software lead, and I'm a computer engineer.
And my name is Alexa. I'm a computer engineering major, and will be the hardware.
So here's an outline for the things we're going to present to you today. We're going to be talking about how we got interested in smart locks and our motivation behind our project, and we'll also talk to you about the design and how we are planning to implement our project.
So our goal of Codec is to create a smart lock service that will aim to solve a lot of the problems that currently plague the technology, which is namely a lack of secure features on modern smart locks. Our design objectives are to make smart lock technology safer and more secure, as well as making smart lock security to a service that we then can provide to numerous different devices on the market. So to do this, we are proposing the solution of introducing a level of encryption that takes place between the database and the BeagleBone which we'll use, while using our mobile application as a system bus that will connect our mobile devices to the BeagleBone. So the market currently with smart locks is very saturated. There's many options available, but many of them are either too expensive or they're very cheap and don't provide adequate security. Two examples that we picked that are on opposite ends of the spectrum are the AUG Smart Lock Pro Plus and the Tap Lock. While both feature user compatibility and friendliness, such as the mobile application is very easy to use, and they're also compatible with iOS and Android devices, they have limitations. For example, the Smart Lock, the AUG Smart Lock Pro uses 256-bit encryption, which is a good standard. However, it's very expensive, upwards of $200 and $300 just to purchase one. And then you have to take into accessories that they also make you buy. Well, the Tap Lock uses 128-bit encryption, which has already been cracked. And even the MAC address of the device itself is broadcast over the network. So smart lock technology is now entering mainstream usage and is just one part of the Internet of Things. So again, there's a lack of secure and safe features in place in modern devices, which puts users at risk for data loss and breaches. And this affects everyone from homeowners with their front door access to business owners and government facilities. And by providing a more robust security system, we can then provide these users with safety and a reliable system that will protect their data. So in terms of our system requirements, we broke it down to the engineering and market requirements. So for engineering requirements, we want high performance, robust security features, connectivity with our BeagleBone, which we'll be using both Bluetooth and Wi-Fi. We want to keep the cost as low as possible, and we want compatibility with mobile devices. For our market requirements, we want it to be easy to use so that customers can just pick it up and be able to implement it on their own. We want it to be compatible with devices they already have. We want security to make them feel secure and safe. We want it to be reliable so that their data is not at risk for any breaches. And we want it to be economic. So by providing a service, we can lower the overall price of the market. This is our engineering turnout picture. So we took the engineering and the market requirements. Based on this chart, the gist is that as we add more and more desirable features, such as better connectivity and compatibility, and of course higher security, the overall cost of the design will increase, which is something that we want to mitigate as much as possible. This is our analytical hiring process. After doing research, we took the most desirable features that we felt were most important in our design, such as security, cost, ease of implementation, and connectivity. We assigned values to them based off of their importance, and our weights were calculated. And from here, we can see that security holds the greatest weight of 0.481, which proves to us the paramount need to improve upon it, followed by the connectivity of the system, ease of the implementation, and the cost.
So here we have a great picture of our system works. We have our two mobile devices, which are the home device and the guest device, which connect to the BeagleBone through the Android application. And the BeagleBone sends data to and from the database. This is also where the encryption and decryption process are happening. Since the possibility of our system getting hijacked, it will report mainly here on the communication to the BeagleBone and database. After this encryption process has been completed, the Beagle Phone returns via Bluetooth the correct tag information to the guest device, which proceeds to unlock the smart lock through near communication. For our related theory, we are using a linked list. Our tables in our database follow the concept of linked list to organize data. We are also using the pseudo-random generator that uses math formulas to generate a sequence of random numbers, and we've chosen this algorithm since it generates largest amounts of the sequence in a relatively short period of time. We are also using the MD5 hashing algorithm to protect the integrity of the user password, since it save passwords as plain text on a database. And for main encryption, we are using the EECE410 algorithm, since the EECE410 has already been hacked. Also, the EECE410 reduces the memory power and processing power, which increments our throughput by 230% in comparison with EECE410. So for our behavior model, our whole system starts on a database where the tables are initialized, and we generate a random key. Then we try to reach connection with the Beagle Phone. If this is not possible, we go on loop until connection is established, and we send the tag information and the random key separate. And once we are on the Beagle Phone, we open Linux OS, and the encryption process starts. And once the encryption process begins, we get a digital envelope as a result. Once the digital envelope is created, the Beagle Phone starts looking for devices. It can find 20 mobile devices, which are our home device and our PS device. Our home device, once it connects to the Beagle Phone, goes through an authentication process in the app to make sure it's the right person. And connection is not established until this authentication process is completed. Once the authentication process has been done, the connection is established, and the home device have the capabilities of set permissions on the database, and the Beagle Phone receives the digital envelope from the database with the updated and encrypted information. We also can find the guest device, which goes through the same authentication process before reaching the connection. Once the connection is established, the Beagle Phone decrypts this digital envelope with the correct tag information to yield the tag information, which is sent to the guest device via Bluetooth. And once the guest device has this tag information, it enables the near-field communication model. Once this model is enabled, the only thing it does is just sends the tag information to the log, and the log reads it. If it matches, it opens, otherwise it's denied access. So for our function models, we have divided our system in two levels, level 0, 1, and 2. The level 0 is the encryption level that happens on the Beagle Phone, as mentioned before, under EECE410 algorithm. The Beagle Phone takes that information from the database and encrypts it, and we have a secret element that's set. For our level 1, we have the communication with the devices, the home device and the guest device. As mentioned before, these are connected through a mobile Android application. And as you can see, the guest device receives towards the end the encrypted tag information from the Beagle Phone via Bluetooth, but still on the app. And our last level is just near-field communication between the guest device and the log. Once the guest device has tag information, just taps the log, near-field communication, and it opens. So for our hardware design, we have our Beagle Phone, our smart lock, and our NFC module. Our Beagle Phone, what it does is encrypts and decrypts information, and also sends the decrypted tag information back to the guest device. For our smart lock, we will be using a log serving emulator using LEDs to signalize the state of the log. And we also add the NFC module to this log emulator to recreate create a smart lock without actually having to purchase one, which saves us great amount of money in our budget. For our software design, we have our Android app, our database, and our encryption. Our Android app acts as the system boss of the whole system, collecting information from the user and sending it to a database in order to store. Database not only stores information, it also updates depending on the user input. And our encryption, as I said before, we're implementing EECE410 encryption happening on the below one. So this is a video of how our database is working. Wait. So as you can see, we have an instance running on Amazon Web Services. We got an IP address which we have linked to our domain called codec.6.be. Here we're pushing information to our database, our authentication table specifically, and as you can see, we're hashing the password with the MD5 algorithm. So once we push this data, as we're going to see, we are going to open our database, and we're following the HTTPS protocol, as you can see, and we've acquired an SSL certificate that's called Let's Encrypt. And so in order to get a database, you need a password and a username. And as you can see shortly, the password is stored as a text and not as an actual plain text.
So our project is really looking to improve the security of the smart lock field, and with this, security is our highest priority, and it's also one of the greatest factors of improvement that needs to be done in the market. So security and encryption is what we're focusing to improve upon, and is also one of the biggest risks of the market at the moment. And also for consumers, reliability and connectivity and connection times. We don't want to sacrifice the connection time and user experience through a higher security level. So in testing all of our units, we're going to be using white box testing from the database to the server and the encryption. So for the database, we have successfully pushed data on and pulled data off the database. And then for the server to app communication, we're using RESTful services for successful web application services. And for the encryption, we're going to be using white box testing to ensure that consumer information is securely processed through our encryption method. And then once we get to incorporating all of our units together, we want to make sure that all of the connectivity is successful and in a timely order. And then once we get to testing everything as an integrated system, we're going to use black box testing to ensure that everything is working smoothly. So we are currently on schedule for our go-no-go milestone. We have the database secured and it's up and running at the moment. And looking forward into the winter intercession, we're looking to start development on our Android application. And hopefully by the spring semester, we'll have that completed. And then moving into the spring semester, we will be working on the circuit design and the encryption algorithm. And by the end of the spring semester, we'll be testing the unit together and incorporating everything as a system. And then our cost analysis is broken down into the items that we currently have. At the top, we have the laptop, mobile devices, and the software, which is free to use. And then the variable costs that comes introduced are the elements that we need to purchase, such as the BeagleBone, the NFC module, breadboard, jumper wires, and LED, so that we can emulate the smart lock, and so we don't have to purchase one. And it allows us to stay within our budget by doing so. And then the codes, the standards, and constraints of the IEEE, we're looking to uphold every constraint put forth upon us, and we're also increasing our security level by acquiring the SSL certificate and following the HTTPS protocols, and also following the MD5 message digest algorithm along with IEEE's Bluetooth and the EECE410 encryption method. is all standards that are allowing us to have the highest security possible for our system. And ethics, as we're stating, our project is all about improving the security of the current smart lock environment. There's a large lack of companies that are trying to provide products that aren't securely holding down consumers' information, and through their faulty use of their encryption algorithms, they're putting consumers at risk. So our project is really looking to improve upon that security and improve the ethics of the current smart lock field. And as I said before, we're on track to complete all of our work. We currently have our database up and running, and moving forward, we're going to be implementing our Android application over the winter intersession and looking to complete our circuit and encryption in the next semester. And these are our references.